So my name's Eric Miller. I'm a consultant. I've been working in IT since about, I don't know, Devin, when did we build my first computer on the living room floor? 2000, 1999? So about 20 years. Since about 2009, I've been focusing mostly on the cloud, cloud architecture, CI/CD workflows for development teams, stuff like that. So in my day job, I spend my time working with really big and really large quantities of computers far away. Don't really know where they are. And so on the weekends and evenings, it's fun to play around with these tiny little computers that we can touch, which I miss a lot, right? Those of you that were, sort of racking and stacking servers, it's fun to touch systems. We don't get to do that anymore with the cloud. So that's what we're going to talk about today, is these tiny little systems and the development frameworks, particularly in the context of open source software and open source licensing around the Internet of Things. So that's me. We already talked about that. Not interesting. So the subject matter is Internet of Things passed through the filter of open source. And so we'll spend maybe 3 or 5 minutes talking about what IoT is and sort of a timeline. Then we'll drill in a little bit to open source and IoT, specifically hardware. I have brought some stuff to sort of pass around, show and tell for you guys to look at, little bits and bubbles. What'd you call this, Devin? My nerd box of holding? Yeah, that's what that is. It's a saving throw you can throw against the box if you want to. And I also have a little demo that we'll do if we have time. All right, and like the previous speaker, who was here for the children and code session before? Yeah, that was great. I really like that. Like that session, please feel free to stop me or just interrupt and say, let's have a discussion about this. Doesn't necessarily have to be me standing up here, wall of texting you guys. If you want to say something or have a comment, or if I get something wrong, feel free to jump in and correct me or share your thoughts. So let's level set a little bit. What is IoT? Everybody knows that IoT stands for Internet of Things, but what's the story? What's the backstory? How did we get to having this in our vernacular? So 1999, a guy named Kevin Ashton, who worked at Procter & Gamble right down the road, he did an internal presentation talking about linking the idea of these, at the time, new RFID tags being put on their products to track them through their supply chain, right? And so that is where the term Internet of Things was born from Kevin Ashton's internal discussion with Procter & Gamble back in 1999. I also like this quote by this gentleman by the name of Neil Gross. This was in Business Week. Now keep in mind, this is 1999, and this is what Neil had to say. I don't know if you guys can see this, so I'll read it out loud. In the next century, planet Earth will don an electric skin. It will use the internet as a scaffold to support and transmit its sensations. The skin is already being stitched together. It consists of millions of embedded electronic measuring devices, thermostats, pressure gauges, pollution detectors, cameras, microphones, glucose sensors, EKGs, electroencephalographs. These will probe and monitor cities and endangered species. The atmosphere, our ships, highways, and fleets or trucks, our conversations, our bodies, and even our dreams. Now, considering what was going on in 1999, and what technology was telling us about what it was capable of, that's a pretty amazing sort of bit of these people who can do this, that see the future and predict it with such accuracy, they always blow me away. And he really nailed it, right? That's really where we are today. We are donning an electric skin. And what we were doing in 1999 did not look like we were headed in that direction. The best we had to offer was, not great. So the real IoT, according to Cisco, and I like this definition, according to Cisco, the real IoT was born, though, in around 2008 and 2009. And this is the point at which there actually became more things connected to the internet than there were people. So I think that's a really good definition. And the moment the things take over, then it really does become the Internet of Things, right? We sort of get subjugated to the things, and it becomes their internet, right? Also, too, just about 3 years later, IPv6 was launched publicly. And that's obviously going to be a big enabler for IoT, because IoT means millions and billions of things. In fact, in my day job, we deploy IoT platforms for companies that have tens of thousands or hundreds of thousands of these endpoints. And so the IP space being diluted is a big problem. So IPv6 solves that. And I didn't know this until I was preparing for this, but IPv6 allocates 340 undecillion. I don't even know if I'm saying that right. Any mathematicians know if I'm saying undecillion right? I am? Guy back there's nodding, yep, you got it. Undecillion, 340 undecillion discrete addresses. So I was interested in that, what an undecillion was. And in the context of really big numbers, here's million and billion. Here's, everybody knows Google and Googleplex, the biggest named numbers, right? Googleplex is 10 to the 10 to 100. Undecillion is 10 to the 36. It's a really, really, really big number that we're considering here. In fact, it's a big enough number that it's enough to assign a single address to every atom on the surface of the Earth and still have enough addresses left to do another 100 plus Earths, right? So we are ready for IoT with IPv6, right? And that's a good thing because these big numbers are coming. These are real statistics, 6.4 billion connected things in use in 2018. That's up 30% from 2015. And we are estimated to, projected to hit 21 billion connected devices, so roughly 3 times the population of Earth by 2020. Let's hope these things don't get guns, right? Or something else smart, right? Because we're whipped. All right, so pop quiz. If IPv6 supports 320, whatever those were, undecillions addresses, how many addresses, without Googling, I'm watching you, how many addresses roughly, rounded to the nearest million, wouldn't it be the guy who knew how to pronounce undecillion that's raising his hand, right? Is there anybody else who knows the answer to this question? What's that? 4 billion. 4.2 billion, and for that, you are going to get one of these boards, sir. That's the, or I could validate your parking. Take your pick. So yeah, so you think about 4 billion. 4 billion is a pretty small number, right? Like that's a number we can actually comprehend. It's the number roughly. It's almost, or I don't know, was it 7 billion we have on planet Earth people? It's a real number, right? This other number of devices is inconceivable. It's like trying to conceive the size of space. As far as the arc of, I've lost my mouse. That's not good. There we go. As far as sort of the arc on the hype curve, this is IoT in 2011. It was on its way up, and this is with all this hype curve is sort of something that like Gartner and other companies use to sort of gauge like what's real and what's going to have legs and stick, and what's just sort of emerging tech that hasn't really proven itself yet. So IoT was on the way in and on the way up in 2011, and it peaked in 2014. And honestly, I think that now, you know, this is more about hype than it is about longevity. Now I think IoT has just become, you know, it's like unleaded gasoline, right? It's here to stay, it's gonna grow, and there's lots of opportunities. So here's me, here's my little sort of like, how did we get from, you know, not having a term for IoT to 20 years ago, when Kevin coined his term, to needing that term? Because those of you who work in this industry, you know that having these systems talk to other systems, M2M, machine-to-machine, distributed systems, connected systems, whatever you want to call them, that's not new. We integrate APIs with APIs all the time. That we didn't need a special word for that, so why do we have the special word? What's the impetus behind that? Well, I think it's 3 changes. It's a series of changes that happened in 3 major buckets: technology, people, and business. Now the technology is really the main enabler, and it's really about compute getting smaller, batteries getting more efficient, more reliable, easier to charge, and also network becoming, you know, who remembers when you needed to look at a coverage map when you were like buying your internet connectivity, right? Yeah, you don't have to do that anymore. Like if there's people there, there's internet. We have internet at 30,000 feet. We have internet in the ocean. We have internet, you know, on the tiniest island in the Caribbean when you go on vacation. It's everywhere. So those 3 things, the compute getting smaller, faster, and cheaper, battery technology improving, and networks sort of becoming more ubiquitous and more spread out. What technology drove that? It wasn't IoT. What's that? Yeah, that was part of it, but what was the major, like what were we buying a lot of as a society that drove those prices down? That's right, everybody's holding their phones up. That's exactly right. Cell phones, mobile connectivity, particularly smartphones, because the smartphones have that magical requirement of needing to drive a display and be able to do smart things and run applications, so they need a little bit more processing power. So smartphones are what drove, or what enabled IoT. We bought billions and billions of these things. We got really good at making chips and the die processes smaller and faster and cheaper. We got really good at making batteries that are small and last a really long time and are easy to charge. and we got really good at canvassing the entire world with network, and where we don't have network, we can spin up networks like LoRa, or even satellite connectivity. Somebody's laughing at LoRa like I had a bad LoRa experience. Right on. Yeah, that's not unheard of. But all these network connectivity options, that's really what enabled IoT. And then also people. So 20 years ago, if we had been walking through like Home Depot together and walked past a refrigerator that was, that was Wi-Fi enabled, we would have, first of all, it wouldn't have been there because it would have been cost prohibitive. It's not a retail, that's something that like you buy in Abu Dhabi and there's 5 of them on the face of the planet, they're gold plated, right? But if we had seen that in Home Depot, we would have looked at each other and said, who in the heck needs a connected refrigerator? That's ridiculous. I mean, that's back when I had a flip phone, right? But this guy's I got one. You got one now, right? But today, we've changed the way we think. Like, we are so connected. We are so used to connected things. We are so used to being able to order on a screen. Like, we've changed how we think about connectivity and being connected at like the DNA level as a society. We are very familiar and comfortable with apps, right? So like downloading an app to work with my refrigerator or my toaster oven or my doorbell or my thermostat, that's not foreign to me or anybody else, right? It makes sense. 20 years ago, it would have been crazy, right? People would have been like, you really have a fridge that you have an app that you manage? What is wrong with you, right? That changed. And then the third thing was with all of these, with compute getting smaller and cheaper, businesses want to differentiate. They want to be able to bolt on new features to their products without having to cut into their profits too much, so that you don't have to buy a gold-plated one and there's only 5 on the planet. We don't make money selling 5 things. We make millions of money selling 500,000 or 5 million things. So we want to be able to bolt on new things, and that's where we saw things like the doorbell and the thermostat, Nest and Ring, and all these real IoT products. So those are the 3 things that changed. People, technology, and business drove this. But really, the biggest change was that cell phone and the millions that we bought and the infrastructure and the capabilities to build these things cheap that came along with that. All right, so let's drill down a little bit. This is Linux Fest, open source event. I'm going to talk open source, right? So let's talk about IoT through the lens of open source. There's a lot to talk about, so we want to make sure that we know that this isn't really a big chunk of IoT. It's actually a smaller section, but we want to talk about it because it's interesting and relevant for this. So everybody here, I think, knows that there's an open software initiative, right? This is a Linux, otherwise we wouldn't be here, right? Linux event, very much tectonic in the open software community, right? But many people are surprised to learn that there is an open hardware initiative as well. Raise your hand if you knew that already. Okay, so about two-thirds or three-quarters, good. They have their own, and I've completely lost my mouse here. It's really, really annoying. They have their own organization. They have their own logo. In fact, we can go, see if I can get out of, there we go. Bad things are happening. Sorry, guys. My mouse is just not visible, and I don't know why. My mouse is visible on the screen. Okay. Occasionally visible on the screen. So now, oh, there we go. I have it back. Awesome.
Part of the top and bottom of the screen are being completely cut off.
I'm going to end the show so that, there we go. I think that's the problem, is my Mac was struggling to deal with that. So I want to show you here real fast the Open Source Foundation website, and they've got a certification process. You can contact them if you've got a hardware project, either a personal project or even like a semi-commercial open source project like Red Hat, right? Red Hat is a business, but they also have an open source project, the operating system. So you can contact them and have them certify your project, and then you can start using this little stamp. You can get that silk screen onto your boards or on your project, or use it on your website. Out of that movement, there are actually some things that I'm sure you're familiar with, right? How many of you have heard of an Arduino? Right? I'm going to pass one around here in a few minutes. Arduino is completely open source. What about a RepRap? Fewer people, I'm guessing, yeah. RepRap is a 3D printer that mostly can print its own components. So once you get the first one printed, there are some metal components that you buy sort of off the shelf, but then one can make many of them, and they're really high quality too. Raspberry Pi, everybody knows that, open source. Also, interesting, SparkFun and Adafruit, which I think many of you are probably familiar with, hobbyist electronics retailer online. They were both sort of founded in this concept of everything that we build and sell, we're going to publish the schematics online. So right at the point of sale, where you buy the thing, you could also download the schematics and like, if you didn't want to buy it and have the capability to build one, you could, or build it on a breadboard. Why that's useful is we're typically going to use these types of boards, development boards, to prototype something. It's not common that a real enterprise IoT solution is built off of an Arduino or Raspberry Pi, like out of the box. What a developer will do is take that platform if it's suitable, and they'll breadboard around it and get it working, and then they'll take the schematic that they have, because it's open source, they'll rip out the parts that they don't need, they'll add the parts that they do need, have an electrical engineer do that, and then they'll send off Eagle files to a PCB fab place, and then they'll have their thing come back that might have the same chip, power supply, and USB serial as a Arduino or a Raspberry Pi, but then it has other stuff on it that they added for their solution, right? So that's why this is really important, and why companies like SparkFront and Adafruit are really cool. Now let's talk about, especially in the context of hardware, how open source is it? So it's not like, you know, Linux software or completely open source software where they have really strict rules and everything that it references, everything in the, I'm sure there's some of you that could teach classes on like the different licensing. I'm not an expert on it, right? I just kind of, there's more people, yeah, raising their hands. But in the hardware world, that's really hard to do, to have something that is like completely pure open source. And that's mostly because of the chips, right? Atmel chips, the ARM chips that we put on Raspberry Pis, the ESP32 chips that we're going to talk about today. You know, those companies they're commercial and they're competitive and they don't really release their stuff. But a company can still have a proprietary solution and have an open look and feel. Lots of development frameworks and lots of development boards where the components are open and available, but the actual, you know, chip schematic is not. So there are some gray areas, particularly Arduino, Raspberry Pi, ESP boards. These all have the open hardware stamp on them. All three of them have at least one component that's not open, right? And there's also some other boards, like these like this little guy here. This you can get in China, not with the OLED, but you can get them without the OLED for about $2 each in packs of 20. And it's an ESP8266, and we'll talk about here in a second. These are all made in China, and they don't, you know, they're not really big on open source. And not that they're anti, they're not explicitly going through the process of getting their chips or their boards certified. But they don't really do anything to hide the schematics from you. In fact, if you ask them for them, they'll give them to you. And if you can look, you know, this is all surface mount components, and there's not a lot going on. You can figure out what's on the board. So it's kind of a weird space. It's not really exactly analogous to software where we have these real strict rules and real strict licenses. It's more of a kind of a Wild West, but there is a lot of open stuff going on. All right, so let's drill into the hardware. I'm really glad I got my mouse back. That would have been really, really tough to finish this. So this is a little blog post or something that somebody did that does a really good job of articulating what development boards are available in 2018. And I'm not going to go through them all. Certainly every board that we're going to talk about today, Raspberry Pis, Arduinos, ESP32s and 66s, the Intel Edison is on here. But I just want to quickly show you like all of the boards. This is pretty comprehensive, and all of the units, some of them have Wi-Fi, you see some antennas on there. There's a big, that's the Edison, right, which is a really powerful development board. So the dynamic here is very much like a craftsperson, right? When who here does like woodworking or other types of crafts with your hands, right? When you start a project, you have a plan, and you're going to need materials and tools to build that thing, right? And you don't really go grab the tools before you have the plan. Well, same thing with the IoT project. We're going to talk about battery consumption. Does it have local network available, or do we need to have some other type of network connectivity? Are we going to have hardwired power? What type of processor does it need to have? Does it need to have any type of battery management or low power mode to save battery, right? These are all questions in your plan, and then you go grab a tool that is suitable to execute the plan that you have. And there's a lot of overlap between these tools, okay? So lots of choices. And by the way, all of the links and code and everything that I'm sharing with you guys today, I haven't put it on a GitHub repo yet, but I will. And afterwards, if you want to come up and I'll give you my email address, and you can email me, and I'll send you the link to the repo. I literally just finished this like in the hallway this morning, so I haven't had time to post it. But by all means, let me know, and I'll give you all that stuff. So today, we're going to focus on these boards here. The ESP, this is a company called Espressif. So the ESP8266, which this is, and these other ones are, is sort of the Honda Civic of the IoT world. Now these are real grown-up chips that you build real grown-up IoT solutions out of, right? This is the, there's millions and millions of ESP8266s out in the field running production code and delivering IoT data somewhere, right? I don't know, 3 years ago, Espressif came out with the big brother to the ESP32, ESP8266, which is the 32. And let's take a quick look at the difference between the two chips. It's substantial. I don't know if you can see that very well. You probably can't. I'll go big screen for a second and lose my mouse again probably. Hey, I kept it. So this thing has, the ESP32 most notably has Bluetooth, whereas the 8266 does not. It has twice the clock speed. It has some SRAM and flash, neither of which the 8266 has. It has nearly twice the GPIO pins. So GPIO pins are these little pins that we use to interface with the outside world. So if we want to hook up an LED or another sensor or an accelerometer, we do that through here. And if we want to have some solenoid switch or turn on a light or a fan, we would also do that through the GPIO. This is the general purpose input and output. And the 32 has almost twice as many pins, which is really a big deal, right? Because you can get a lot more sort of value out of the chip than you would twice the value. It also, and we're going to see this here in a second, this chip itself, not the board, the chip, just the little tiny square that you see here, has 3 onboard sensors that this 8266 does not. It has a Hall effect sensor. Who knows what a Hall effect sensor does? What's a Hall effect sensor do? Measures magnetic field, right? This chip has one on it. We don't need to bolt it in through GPIO or put it on the board. It's right there inside that little tiny can. It has a temperature sensor. It's not a really good one. It's not consistent from board to board. And also, too, this can on the outside, which doubles as a heat sink, kind of prevents you from making contact with it. So it's just, I don't know why they put it on there. It was dumb, but it works. And they have a capacitive touch sensor. So we can assign capacitive touch to one of these pins, which is basically mapped to one of the pins on the board. And then we can touch it with a hand, and the board will know that it's being touched. This is useful for things like you could wire it to a door frame. Of course, we're talking about not wiring this board. You build a finished system that is a box that you mount to the wall. You wire it to a door frame, wire it to a desk, and you'll be able to tell if someone has touched that thing and how many times. Same thing with the Hall sensor. Just by mounting a very small device, about a third of this size, to a door and putting a magnet, you can tell how many times the door's been opened, whether the door is currently open or closed, things like that. Without ever bolting anything, just with the processor itself, not needing any peripherals. So let me share with you guys some hardware. I'll tell you what they are, and then I'm going to pass them around in this little. This is from our CSA. It's got real high-tech anti-static stuff in the bottom of it. Brandstool orchards. So we've got a lot of cool stuff in here. We've got 2 Arduinos. I think you guys will recognize those. These are the blue ones, right? We've got an 8266 with an OLED on it, right? That we can power up, and it would have like a little logo. We can output data to that. We've got a tiny little teensy, which is an Arduino board, which now belongs to you, right? So you can keep it when it gets to you. Or we've got a Raspberry Pi Zero, which is a great development platform for IoT, especially if you can leave it hardwired to power. And we've got this Iotanium board, which is something that one of my coworkers developed from scratch. This is his own design, and it's an ESP32 board. The one that's really interesting, and please be careful with these. I mean, you can touch them, and you don't have to worry about static or anything, but just be careful because they'll break. The one that's really, really special to me, though, is this one here. I need more hands or more real estate. The one that's really cool is this one here. I'll show you why. This is just an 8266. There's no power, there's no USB. It's literally just like buying that chip from Espressif and putting it on a breakout board and getting the chips broken out to pins, right? That's it, there's nothing else on the board. And I like this because it helps kind of build an intuition. Like you plug this into a breadboard. Unfortunately, they designed it so if you plugged it into a breadboard, it covers up all the pins. So I need to build this wonky adapter to make it work. This is just a USB power supply, so it takes the place of a lot of the circuitry that would be on a finished board. But there's no USB to serial, there's no power supply, there's no GPIO pins. It's just the chip. So when you fiddle with this, you really get a good intuition of like what the chip can do because you're only interfacing with the chip itself. This one I used to build a nightlight with my kids. It runs a little web server, and then you can hit that web server. We have a DNS map to the private IP of this thing, and we put it inside a 3D printed Minecraft cube, right? A Minecraft block. And those of you, how many of you know what this thing is? Yeah, it's about a quarter. Right? So this is what you build stuff out of in Minecraft, or some things, and it comes in different colors. Red is redstone, blue is lapis lazuli, right? Let me get this wrong. And pink, they say, is some kind of like nether crystal or something, right? But every time they hit this endpoint, they can get their iPads out and they can just go to nightlight.millerhouse. You can't get on my network, so it's fine. Nightlight.millerhouse. Something, I forget. And they refresh it, and they get a new color every time they refresh it, right? And their interface looks like this, and it tells them what they get. So I'll pass this around too. And you guys can just look at this while I'm gabbing. There you go. Yep. So that's what you have in your hands there. That's just a small sample of what a hardware developer, hold on a second, what a hardware developer or an engineer would use to start a project, right? Depending, again, talking back to that slide, if it's the right use case, right? We're not just going to grab any board just to address any problem. You have to kind of look at the parameters of the problem. Yes, sir. You with the blinky ears.
We can't actually see what you were.
Fantastic. That's really helpful. There we go. Perfect. So I'll go back. Here we go. So here's the nightlight, the 3D printed nightlight. That's what it looks like in its case. And it's just paper inside there. And then that little unit, that ESP, that breadboard, that's what's in the black box here. And then it turns red for redstone, blue for lapis. And it does like 17 different, we did all of them, right? And this is what their interface looks like. But that little web server, that's running on that tiny little chip, right? This HTML is coming from that chip. It's really, really, really cool.
Where did you get the files to 3D print that? Did you make that up yourself?
I found the cube files on Thingiverse and just kind of hacked them up a little bit because they were, I needed the bottom shaved off to get the stuff inside it. I have the STLs though, and so if you come up afterwards and give me your email address, I'll send them to you. Right on. And I also have the code for it too, so if you get an 8266 or a 32 dev board, you can just plop this stuff on here and it'll work for you. All right, thank you so much for telling me that you couldn't see my slides, or couldn't see the other stuff, right? That would have been pretty bad. So let's talk about development frameworks, right? This being open source, right? So development frameworks for IoT are broken up into sort of 3 tiers. We've got what goes on the device. Today we're going to talk about microPython. We have what goes on the gateway. So it's very common to have a gateway device that sort of shepherds out connectivity like a wireless access point, right? But specifically for IoT, that shepherds out connectivity to lots of local devices, aggregates that data, and then sends it to some endpoint in the cloud. And then we have the cloud backend, right? By the way, we're going to build a solution today on the cloud. In 2018 and beyond, there is absolutely no good reason to build IoT solutions in the data center on physical spinny drive hardware. That is dumb, right? Somewhere between dumb and just technically impossible. And the reason is your devices are going to scale up and down the amount of traffic that they send to the cloud, and you don't want to be paying for full capacity all the time. You want that to scale up and down with it. So we use a cloud service so that we're not managing infrastructure instead of just getting the data we want. So it's important to point out, though, that of these frameworks, that C, we use, you can see these are C, C++, Python and MicroPython, Java, JavaScript, and PHP, that there's a lot of open source representation here. The GNU implementation of C is open source, as is GCC, the compiler. Java has an open JDK. Python and MicroPython, both 100% open source. PHP is open source. Did someone raise their hand? Did you have something to say? No, just yawning. Sorry. PHP is 100% open source. And C++ and JavaScript are not technically open source. They're overseen by a standards committee, so they have kind of an open source look and feel because they're an open standard, right? But they don't adhere to an MIT license or anything like that. So a lot of openness represented here in the frameworks that we have. Today we are going to be zeroing in specifically on MicroPython. I like MicroPython because I have a background in Linux and Unix administration, and Python was sort of a natural jump for me from Bash, right, to do stuff that Bash couldn't handle. And so like many of you who are Linux people, I think Python is a sort of a great utility language. It's also being used, it's actually become the most used language in the industry right now because of machine learning. It's the de facto language for data science right now. So if you don't know a language or you're considering learning a language, Python's a really good place to start because it's widely supported and it's really the de facto language of data science. But we can't put Python 3 on a tiny little microcontroller. It's way, way too heavy, right? So we need a special version of Python called microPython. So we have that, and it's about 4 years old now. It was started by a guy named Damien George. He had a Kickstarter campaign. There was a board that went along with it. It's written in C. It's released under the MIT license. It's completely open source, and it's a full Python compiler and runtime that runs on the microcontroller hardware itself, and it presents the user with a interactive Repple. Repple, we're going to say that word a lot, so I want to make sure I share with everybody what it means. It's a read, evaluate, print loop. Did I get that right? Is it read, evaluate? Yeah, read, evaluate, print loop. It's those of you that know Python, it's the 3 little arrows that you get when you log into a Python system, or when you open up Python. So that's MicroPython. And in a minute, we'll look at the MicroPython repository. But here is the different ports that they have available for MicroPython. And you can see they have the 32 and the 8266. No Arduino, because Arduino doesn't really have enough resources to run MicroPython. All right, so it's time for everybody we're going to do the demo. And before we get started, this is a live demo at a tech event. And so what that means is everybody just take a moment of silence, okay? You do your thing, I'm going to do my thing. All right, we're good, I think. We'll see. All right, so what we're going to build today, this is what a real IoT solution looks like in the cloud. We start with devices, hundreds, tens of thousands, millions of devices, and they all have some sort of code running on them that gathers data and sends it to the cloud. Sometimes we'll send data back to them to tell them to do things. We'll have some sort of authentication so that not just anybody who has knowledge of the system can start, if you fire me from your team and I can start sending stuff to the cloud, you don't want that. It has to be secure. And then we have a device gateway. It's an endpoint that we're going to send the data to, that then once it's in the cloud, we can do whatever we want to with it. We can trigger Lambda functions. We can put it in a document store. We can put it on S3 or some other blob storage. We're not going to show that today. We're just going to show these 3 nodes, right? Real quickly, just want to point out, I know we're using a commercial cloud provider to build this today, which is AWS. But I just wanted to point out that there's a lot of open source support on AWS for this stuff. So we're using MicroPython on our chip. We're using MQTT, which is an open standard to send our data to the cloud. And then once we get it to Lambda, it's any one of several open source or open frameworks, Java, .NET Core and PowerShell, Python, Go, Node, which is JavaScript under the hood. Those are all fully supported. So even though we're in Commercialville for who's hosting it, we don't lose the open capabilities to do our thing. And that's what this slide was supposed to sort of open. I got ahead of myself there. All right, so for the demo, what we're going to do is I'll show you how to build MicroPython. I'll show you how to flash the board. This is basically what you would do if you got a board in the mail from Adafruit or went over to Micro Center and bought an ESP32 board. What would you do on your first day of playing around with it, right? You get it out, you want to put MicroPython on it. You want to connect over serial. I'll show you some helper libraries and what they do. I'll show you how to connect to the web REPL, and then I'll show you how to upload scripts, and then eventually we'll connect it to a cloud service, and we'll see data flowing to the cloud. Now before we do that, I just want to make sure that my cloud service is still accepting my connection. Oh, thank you, cloud service. Okay, so the first thing we want to do, and I'll be going back to this to keep me on track here, is we want to build MicroPython. Now, like many of you, how many of you are software developers or engineers? Okay, so about 15%. I like to, when I set up build environments, I like to set them up in separate somethings, right? So a separate machine, Vagrant, VirtualBox, whatever, Docker, because I put tons of stuff on my local workstation, and I like to have like really predictable results from builds. So I set up Vagrant to do my builds, right? So what you're looking at here on the left-hand side of the screen, this is my Vagrant environment, and I have basically just cloned the Windows, oh God, did I just say that? Here come the tomatoes. Bad crowd for that one, man, wah. I just cloned the ESP32 port of MicroPython to my Vagrant environment, then I can go in there and I can build stuff. It's important to point out that, I want to go into modules here. This is really important if you do this. You can write your own MicroPython, put it in this modules directory, right? do the build like you normally would, and anything that's in that modules directory will be like a first-class module from this Python standard library. Like when your system comes up, if your module's written right, it'll just work. You won't have to import anything or use micropip or anything to get or transfer files. So it'll compile down to bytecode when you do the build, and it'll be available for you on your system when you bring it up. So that's a neat little trick that is very helpful. So in order to do the build, first I would make sure, obviously, that I don't have a previous build. And then and I'll show you where I got this from. There's a little one-liner that I run that passes what I need to GCC, and then it builds. I'm sure many of you have seen GCC. Even if you're not a developer, you've built something, because it's a Linux conference, and we do that stuff. We love to build things from scratch all the time. That's what Linux people do. So I'll quickly just show you where I got that from. Those instructions are here. Yeah. So on the ESP32 port, there's a step-by-step how to set up the environment. I just did it in Vagrant. That's the only difference. You can do it on VirtualBox. You can do it on another VM. You can do it in Docker. Then I set up the environment in the tool chain. I did all this, set up the environment variables, and then I built the firmware, right? So you guys can, and again, I'll put this in the repo so you can get to these links if you want to. So that's how you build microPython, and that's going to produce for us a single bin file, right? Binary, almost like a disk image or an OVF that we would put on a VM. So then what we would do is we'd flash the board. And I'll go back here to this terminal. Now on the right-hand side is where we would flash the board. You see I've got this firmware.bin right here, this little guy. That's what we would get out of Vagrant. Vagrant would produce that build, and we get that binary file out. And this is our little operating system, right? And remember, anything we put in modules is going to be baked in here, so it's going to carry that with it when we put it on the system. The statement that we run to flash the board, there's actually two of them. And again, I'll make sure all this stuff is available for you guys. It's actually two of them. We need to erase the board here. The only thing is you would change this to your serial connection. And then we need to flash the board. And that's pretty much the same command, except we're going to point it to that firmware.bin that we just got out of Vagrant, right? So we build it, we pull it out of Vagrant, we put it on our local system, and then we run these two commands. If you probably are going to need this tool, and so I'll show you where that is. That's here on the ESP, Espressif's Git repo. Remember I said they're very open and sort of provide tools for the community. So that's that. And that's where you get ESP tool. It's just a little Python pip install, right? If you used to Python, you just use pip to install it, and then it's real easy to use. So that is how we flash the board. So after we get our board flashed, you're going to want to connect to it and work with it. So what you do then is you would just find a power source. It works off USB. I'm just going to connect it to my board, to my laptop, and it works just like that. Plug it in, and now I should have a serial connection. So I'll just open up another terminal window. And now I'll make this big for you guys because I realize you probably can't see it. There we go. And then I'll connect to it. Hey, look at that, microPython on a tiny, tiny little computer. And this never gets old for me. I always feel like Bob Ross when I'm doing this, oh, happy little microprocessor. That's so, hi guy, you're awake, That's just now, every time it happens, I'm just like, that feels awesome, right? Because, think about it. I have a serial connection. Forget the rest of the board. I have a serial connection to just this little chip right here, right? And I'm running Python. I can do anything I want to that I can do with Python. It's really fun and exciting. So that's our REPL connection, and we can do something like, oh, we don't want that. Hey, print. And we're in Python 3, so it's Python 3 syntax. And we're at Ohio Linux. Awesome. Now that's what it looks like. Not very interesting, but we'll do more here in a minute. So now we've built our code, we flashed our board, we connected serial, and we've seen the REPL prompt. So now let's look at this little helper library that I built. So I didn't want to bore you guys with a bunch of typing, right? Because I probably would mess it up, because it's live and I'd always get it wrong. And in the REPL, those of you who've worked in a live REPL, if you get it wrong 3 steps down, you got to start all over again. So it's like asking for trouble, and I didn't want trouble. So what I did was I wrote this little library. Where are you, library? Yeah. So what it does all kinds of stuff. When the board comes up, it will try to connect to Wi-Fi. So I gave it the Wi-Fi connection to my phone. It will enable the access point. It has its own Wi-Fi access point, so if it can't get on organic Wi-Fi, it will spin up its own AP that I can then connect to do stuff if I don't have a serial connection. It also has, remember, that temp, that hall, that touch that's touch sensors. I made some little helper functions for that, so you don't have to watch me type all that stuff. And then we can read all of them if we want, and we can toggle LEDs on and off with these little helper functions. And again, I'll make all this stuff available to you guys. So let's just do that real fast. Let's do, and Iotanium is just the name of this board. I could have very easily called this board, called it board or whatever. So don't pay any attention to that. We'll do Iotanium. So this LED is this one up in the upper right here. I think you could probably just barely see it. It's currently on, so what I want to do is I want to turn it off, right? And I'll hold it up and you'll get to see, did it go off? Yes, yes. And then I can make it go back on. There it is, back on, yeah? And then we can do this. It's going on and off. Nice. Okay, so now we can manipulate the LED. And we could also, too, add this one that we can do, iotanium.blink. And this takes 2 arguments. We can tell it to blink for like a 500 millisecond delay for 10 seconds, right? And that should start to go, there it goes. See it blinking? Yep. And then what else can we do with this? We have the sensors that we can read. I'll just get out of this. 10 seconds was too long. It really bothers me that the Repple does not have a clear function like RealPython does, so I get all the way, who else is like that? Like everything is like do something clear, do something clear, right? Yeah, I have that problem, so this just really drives me nuts. So let's look at some of these sensors. Now remember, it's got a temperature sensor, a Hall effect sensor, and a capacitive touch sensor. So let's try all 3 of those. We'll do iotanium.temp. And again, this is just wrapping up the functionality, the native functionality of the board in little helper functions. It's all in here for you to see how it's done closer to the metal if you want. And that'll give us this temperature reading of 127. We can also do iotanium.hall, which will give us our Hall effect sensor reading. I don't want star, which is currently 82. And then we can do iotanium.touch, right? Which is currently 645. Now what I'm going to do is I'm going to touch a pin, the one that is tied to that capacitive touch. I'm going to run it again, and it drops down to 12. Right, so now we could write code that says when a threshold is below 100, what's that?
You can shrink the screen slightly so you can see the left-hand side. Cutting off the left, right, top, and bottom.
I sure can.
I believe the number is good.
Gotcha. So, so yeah, there it is without touching it, 645, whatever that means. Right? That's just the value that the sensor reads, and I touch it, and wow, look at that. There we go, right, 4. So you could see where we could use that in code to sort of set thresholds for what's, or you've also seen people like maybe assign touch to lots of pins and then put attach fruit to it with cables and then do like a little keyboard, right?
So are the temperatures, when you say call temp, is that to be like a relative term, like it's cold now and now it's warm? Or?
Yes. So the temp is just a raw value off the sensor. It's not a Fahrenheit or a Celsius reading, but you just have to sort of, it's a linear correlation, so you just have to build that into your code. No. It's hard coded in the chip. Yeah, so you could calibrate it, but you'd have to do it in code.
Okay.
Yeah. Sure. Yep. Okay, so that's those are the sensors, and I have this other one too. Let's do this. We can just while true. We'll do iotanium.readAll, and it'll give us all the sensors. There you go. So this is fun. So we can see, I'll do the Hall effect sensor. You can see Hall, its normal state is around 80. I have a magnet in my wallet. So I'll put this on here, and we see Hall drops down to, Hall jumps up to 225 there when I put a magnet on it. Put a more powerful magnet on it, which is over here, I can get a negative reading. So basically the Hall effect sensor is in the middle, and one polarity will pull it high, and the other polarity will pull it low, even negative, if we put the right amount on it. So I'll try to get the temp to go up. The temp currently is saying 128. I'll put my finger on it and see if I can get it to go to 129. Sometimes I can get one, that's going down, yeah. It's a really, really, really bad sensor. I have held a lighter to it, and I can make that work, but I thought that probably wouldn't be appropriate, you know. You get one of those Elon Musk flamethrowers.
If you want to calibrate, just throw it in the refrigerator, have a little thermostat.
Yeah. So that's all the readings coming through at once in real time, as fast as we can do it. So that's fun, but it's not really IoT, right? This is more like hobbyist, like we're just reading sensors, it's wired to my system. Like we want to do something meaningful with this. And in order to do that, we can't do that in the REPL. We're going to need some code. So I have this very, very, very simple, this is basically the, yes?
These functions that you're using in your code, are those in firmware on the chip?
They are. The functions that I'm using in my code are on the firmware because I put them in that modules directory when I did the build. That's right. They're in firmware. This code that I'm showing you now is not in the build. This code is on my local system again, this is just an MQTT client. MQTT is a messaging protocol that's well suited for IoT, and this is how we're going to get our messages to AWS, to our endpoint. And so in 25 lines, and I could have done it in less if I'd combined these two, I don't have any error handling in here, I don't have any object orientation, nothing nice. This is just sort of like hello world to prove the concept simply. We're going to take this test.py, and I've already got it on the board for you, and we're going to import it and run it. Okay, so let me just walk through it one more time. That script that I just showed you on my local system that has the MQTT client, and I'll walk you through it. I should probably do that real fast. What it does is it makes a connection. It establishes the thing ID as the CPU GUID for this device so that we can have some, so we don't have naming collisions up in AWS. It establishes the endpoint. That's the DNS host name of the place I'm sending this data. It reads 2 cert files, a private key and a cert that I've put on this board so that we can authenticate. Remember that authentication node in the thing that we're building? That's how we're doing that. And then it creates a client object using the MQTT library, which is also on the board, and then it connects. Once it's connected, it's going to sleep for a second, and then it's going to take all 3 of those readings, again, just like we did a second ago, but it's going to take them quietly and munge them into JSON and send it to AWS, okay? So we take that file, we put it on the board. When I did that for you already, we're going to do that in a second so you can see how it's done. And then it's doing it in the background because I don't have any logging output because I was trying to keep it simple. So if we go over to AWS now, to the dashboard, and we subscribe to that MQTT topic, which today for this event is Ohio Linux, we will see those values are coming through right now. If you look right sort of here, you'll see that timestamp changing, right? Right there you can see it changing. You don't see the values changing too much because I'm not changing them, but let me just do that real fast with the Hall effect sensor first. You'll see the values change up in AWS. So now Hall's dropping to 79. Now it's down to 30, negative 34, right? We can also do the touch sensor. Dry my hand here and touch the right pin. And you see the touch sensor is now dropping to 17, and we're looking at this value right here, right? That's going to change. It's 645 in its normal state. Now it's down to 12, right? And now this is no longer on my system. This is happening up in the cloud. This is just the back end that we're sending it to. Yes, sir?
What does it cost for the AWS?
The cost is negligible for this. You can look at the pricing. I don't know it off the top of my head, honestly, because I work for a partner that does a lot of work for AWS, so we get this stuff for free, and I don't really pay attention to the pricing. But for this service, I can tell you it's negligible. It's going to be pennies on the dollar to like spinning up your own instance and your own MQTT server. Yes, sir?
Just to add on to that response, AWS has a free tier. It's not very beefy, but it's free, so you have something.
Yep. So what I'm going to do now is I'm going to fire up the web REPL. Now remember, REPL is this console that we're in, but they also have a web version of that. And I'll show you where you can get it, and then I'm going to make sure I have it started. And that'll give me this value right here is what I'm after. So this is the endpoint for web REPL, and web REPL, again, is here. It's on the microPython site. You can download it. Thank you very much, sir. You can download it, and it's like, you can think of it like a client. You don't have to go to a website. You can just download this to your local system, clone this, go to an HTML file, and you can think of it like a little binary client to always get on your system. In fact, that's how I manage that little one that doesn't have a serial connector, the one that's just a chip. I flash it with an FTDI cable and put web REPL on it and have it start automatically, and then I always just interface with it and program it over the web REPL. And so you would just open this HTML, and that's what I have over here. And so if I take that file that that value, and I put it in here. I get a password. Perfect. And then what I'm going to do is I'm going to upload a file called main.py. Now main.py is nothing more than test.py renamed. Send it to the device. You see I've got, and this is why doing this over serial is a real pain in the butt, because I have to stop my serial connection and then transfer the file. So now main.py is on the device, and what should happen, now we're going to make a real IoT thing, right? What should happen is when I power this thing back up, MicroPython's going to boot. MicroPython's going to call its boot.py, which has sort of environment setup, Wi-Fi connection, that sort of, whatever you want to put in there. And then it's going to run main.py. That's what it's designed to do. And so if things are going right, I should be able to pass this around the room. And do me a favor, make sure your hands are dry. Like wipe them on your shirt before you touch the pins. The pins are right here sort of near the green. Just touch them all if you want, but just really kind of brush them. And do please wipe your finger on your shirt, otherwise it'll do that little error that it threw earlier. So now, hopefully, if this goes well, we'll have a real IoT device, and you'll be able to see the values change, which you'll need me to do here. Here you go, Devin. So and I'll also give you my wallet so you can do, yep, there's the touch sensor dropping to 24, and then back up to 644. And again, we're looking at these values here, if it makes it easier for you guys to see. These are the values you want to look at as they're changing. And here's that magnet. If you want to also test the Hall effect sensor, just hold either of these magnets. There's one here, hold it right up next to the tin can, and you'll get to change the Hall effect sensor. So just pass that around. So now we have a real IoT thing, right? It's unplugged, it has its own code, and you can imagine how you could build something that you could do whatever you wanted to do, and disconnect it and cut it loose, and now you have real IoT. So where do you go from here? If this interests you, and I hope it does, go watch this video. I'll give you my deck so you can get to this link. Go watch Nick Moore's talk. Nick is a primary contributor to the ESP32 port of MicroPython. This video really inspired me to get more sort of involved with this project. Nick does a great job of explaining how you can contribute to the ESP32 port of MicroPython. For someone like me who's not a C programmer and doesn't really want to be, he really sort of gets you excited about like how you can take functionality that doesn't exist in MicroPython for the ESP32 and make it work. Any of you who like to contribute to open source projects, go watch Nick's video. He's a really cool guy. He's wicked smart. And if anything, you'll learn something, but maybe even get excited about contributing to MicroPython on the ESP32. So that's my talk about IoT in the open source space. Hope you guys liked it. We have just a few minutes left that we can do Q&A if you want, and I'm happy to do that. And then, of course, after they kick me out, if you have any questions, we can talk on the side. So any questions or comments? Yes, sir.
I know you mentioned you wouldn't want to do IoT anywhere but the cloud, but let's say you were doing something in your home. Wouldn't the functionality like drop if you couldn't talk to AWS anymore?
So that's where you use. Absolutely, yeah. Could you, and especially in your home, right? Like that's a good example. If you just want to build something in your house, you can set up your own MQTT. In fact, many of the open source home automation projects, there's two really big ones. They operate just like that. So home automation is a strange space because that's the one place where you would want to kind of keep your network private, and you won't have millions or tens of thousands of things, and you might want to hack on your own little thing. In that case, you would just install an open source MQTT server like Mosquito, or install one of the home automation things that also work on MQTT, and then just use that. So that's a great example of when you would not do what I said. But for enterprise IoT solutions, building them anywhere but in the cloud is basically asking your competitors to eat you for lunch. Yep. Yes, sir.
What's the difference between MQTT and 0MQ?
I don't know. I just know MQTT. I've seen 0MQ here and there. Once I find something that works, I just kind of blaze ahead and go on to the next thing. So I didn't get too deep into that in the messaging space. So I don't know, and I'm not going to give you a baloney answer, right?
Fair enough.
Why don't you find out and come back and teach us?
Sure.
Do a session next year.
Yeah, that'd be cool.
Yeah.
I'll make sure to get you carded.
Okay. Yes, sir.
I assume you've built many Internet of Things projects before. What was your favorite?
So I haven't built a lot. I just got into it about, I don't know, 3 or 4 years ago. I've built a lot of hobbyist systems, just like that Minecraft thing. I built a lot of that kind of stuff on that chip and Arduino chips. It wasn't until about 2 years ago where my work sort of thrust me into those places that I started building more enterprise solutions. I see Scott back there. I mean, I got 5 minutes. Okay. Okay. So yeah, I really haven't built a lot myself, but it's something that I got thrust into at work, and so got really interested in. So when Scott and Werner asked me to come speak, I wanted to do something different that I hadn't done before, and so I kind of said, I gave them 3 topics, and they said, hey, let's do this IoT thing. So I really have not built a lot. Maybe, I don't know, 2 dozen, right? Most of them hobbyist type stuff. But the information I share about how we do it in the enterprise is because that's what I do in my day job. More questions? You guys really, really, really want to go to the bathroom? By the way, you don't have to wait for me to say, you're all like free grown-ups, so you can go where you want, when you want. So go to the bathroom. Yes, sir. 2 questions. You in the front. Yes, sir.
What do you do in the case when you don't have like a Wi-Fi connection? Like you mentioned like satellite internet?
So satellite is definitely a failover that we will design into systems that need it. Give me a use case that won't have Wi-Fi. Yeah, so in the ocean, in fact, we're building a solution like this for tracking shipping containers. The ocean, we'll just aggregate data and do it when we get to ends, right, the ports. But if you need to have real-time data in the ocean, then you need to solve for that. So if the shipping company's not going to give you access to their onboard Wi-Fi, then you got to strap a satellite somewhere on that boat, right? Yes, sir. Yeah, it definitely. I don't mean to cut you off, but I think this is probably the last question I can answer, so I got to drop off because Scott's going to come stomp my head. But yes, absolutely. There is nothing more scalable than Lambda. So Lambda is AWS's serverless compute thing. We didn't talk about it much today because that's it's commercial. But to answer your question, it is highly scalable. 1,000 concurrent executions per region, 15 regions per account, 15,000 times 2 cores, 30,000 concurrent executions without ever raising your service limit. Don't ask me how I know that. Finding those things out is how you get your account shut down for like 3 days. All right, so I won't ask any other questions because I think we got to be respectful of the next group. And thank you guys very much. Appreciate it.